Hello and welcome back to another YouTube video, and in this video I'm gonna solve this problem on LeetCode. It's called search in a binary search tree. I'm assuming you have a knowledge of binary search tree and what it is and what's its property, and if you don't have this knowledge you can view my previous video if you want. I have explained it in Visual Conceptual, and there is a problem called validation binary search tree which gives us a good foundation of how can binary search tree work. Moving on to this problem. We have a binary search tree, we have a reference to the tree, and we have a value, and we want to search the binary search tree to find this value, and if it doesn't exist then we return null. How can we solve this problem? Let's see. Alright, so for conceptual approach we're gonna visualize what we should do. So BST has a really good property, so basically we can use it, we can solve this problem using one question. Is 14, which is the value we want, greater than or smaller than the value presented right now at the current node? And we begin the solution with our root value, which is 10. So is 14 greater than or smaller than or equal 10? It's greater than. So we basically eliminate the half of the entire tree by just dropping it down. And now we have the right side of this tree, and now we ask the same question: is 14 greater than or smaller than or equal 27? 14 is smaller than 27, so we go to the left side. Now we drop down the right part of the tree, and now we have found our node element. So now we'll ask the same question: is 14 greater than or smaller or equal? 14 equals 14. So basically we have found our solution, and that's it for our solution. And now we're going to talk about complexity of this solution. Specs complexity for this solution is going to be O of 1, because we're not going to use any space or any data structure for solving this problem, except if you're using a recursion way. If you're going as recursion, then it's going to take the space of the time complexity. So let's calculate the time complexity. If we're going to use the recursion or iterative approach, it's going to be the same. It's going to be O log of n. How can we justify that? How many steps have we taken from the root value until we reach what we wanted? We were at 10, then we moved to 27, then we moved at 14, and then we validated our 14, and we returned our value at this position. So basically we have taken almost like 3 steps. We have moved from 10 to 27 and 27 to 14, and from 14 we returned this value. So basically we took 3 steps. So it's O log of n, where n is the number of nodes in this tree or any tree. This tree has 13 elements, and we taking this log of 13 with the result of 3.7. So approximation, we have a time complexity of log n. And if the highest possible number is, for example, the highest possible number of leaves, it will be approximation of 3 as well. So basically it's log n. The time complexity of this algorithm is O log n. Either recursion or iterative, it's both work the same way. But for recursion, because it takes from the memory stack, yeah. Yep. So basically it's gonna take the same space. Its time space complexity is the same as time complexity in recursion way. So if you're gonna solve it in recursion approach, then your space going to be O of log of n. But if you're gonna use an iteration way, then it's gonna be O of 1. I myself prefer the iteration way. You can do it which way you can prefer. And now let's get into code. So let's solve this problem. And now I have solved it before just to check my answer. We're gonna check if the root value is not null, and then we're gonna return roots anyway. So let's see. If current value is greater than root value, then we should move right. So So now we're gonna move right. This I'm just gonna copy and paste it with smaller than this time. If the current value, I mean the value we want less than the current node value, then we're gonna go to the left side. If the current value equals the node value, not current, I mean the wanted value equals the current node value, then we just return the current node. And that's it for our approach. It should work fine. Let's see how can it work. Right, approach, I missed it, and I think that's a problem. Yep, we're faster than 100%, and the memory usage is 71%, which isn't really bad. It's really good. Less than 71%. Anyway, that's the solution for our problem, and that's it. I hope you enjoyed it, and see you next time.